Hello everyone, I'm here to talk about how to use large language model to build Bayesian network for fraud detection. Imagine you are starting a bank or credit card company and you have to choose whether to approve or reject each application because you're worried about fraud. This is a hard problem, especially at the beginning when you have very little data. How do you reason about suspiciousness while properly accounting for different traps? To do this well, you have to understand the causal structure. Traps on that previous slide, they are similar to what's being explored in causal T5K benchmark. My goal here is to take that large language model causal reasoning out of a diagnostic sort of setting and into a real application domain, fraud detection, where we can evaluate two things at once. First, how well the model reconstructs the underlying causal graph, and two, how that graph actually performs as a decisioning system. This naturally leads to our core design choice. Instead of asking the large language model for a fraud probability directly, ask it to build a causal graph, then let a tool do the exact computation. Here's the full system description. The first part is building the evaluation dataset for this domain, which is a pretty large lift. We started with taxonomy construction on what is reasonable for banking application data collection process. Note that every bank and fintech work differently, so we try to keep this somewhat generic. Then we need to create scenarios. We elicited additional domain knowledge about fraud tactics so we can see diverse type of fraud. And also there are reasons why legit applications can look suspicious, which is why this is a hard problem. We elicited a large set of possible causes for false positives, just so to make things less trivial and more realistic. And through combination of taxonomy and fraud tactics, we assemble packages of cases with varying complexity. I used the most powerful model at the time, GPT 5.2, to generate Bayesian network across 10 industries and 4 difficulty levels, each with hundreds of observable variables, latent factors, and about 55 inter-observable causal edges on average, and those include mediation, confounding, and different kind of traps. From each Bayesian network, we sample 5 cases via ancestral sampling, and in the end, what we get is a dossier that looks like a human-readable application. And this is what we're going to use to feed to large language model and other techniques that we're testing. The second part of the system is the evaluation method. The primary one I want to cover is Bayesian network construction. We have domain specialists focusing on different facets of the data. They put it together and have architect and a critic loop to debate the causal edges. And finally, in the end, run an algorithm for posterior calculation. Now to the result. Bayesian network construction performs really well, better than machine learning baselines, vastly better than the prompt-only methods alone. Notably finding on prompt-based methods, one, giving the large language model too much information, like throwing all conditional probability into the context window, actually makes it perform worse than a simpler prompt without any statistics at all. Also, getting debate to work here is hard because suspicious stories are easier to make rhetorically compelling than innocent ones. I'm not sure why that is the case, but this is one of the observations. We see that debate has systematically determined things to be fraud. Not surprisingly, multiple rounds improve performance. In our case, we limited to just one round, mostly due to runtime budget. Because we know the true generating Bayesian network, we can evaluate structure recovery directly. Bayesian network construction does fairly well in precision and is good at finding the edge between fraud to observable variables, but not as good at finding the causal relationship between two different observed variables, where it only detected 7 out of 55 edges on average. This is with GPT 4.0. With GPT 5.2, it does 4 times better on structural recovery. However, the classification actually drops. The reason is because as the model complexity increases, the CPT just becomes less accurate due to sparsity. CPT means conditional probability table. Now to the limitation and future directions. First, this is a controlled methodology study on synthetic data, not a production benchmark. And like most evaluation benchmark, this setup traces some external validity for control. The advantage is that we know the true latent factor and causal structure, which let us evaluate both classification and also structure recovery directly. Second, we could have definitely generated more data, so more time and budget to make the experiment on a larger data set would have been really cool. And also on the future direction, we could have used large language for CPT prior for sparse configuration rather than just for structure. This could have helped with some of the problem we've seen with sparsity. And secondly, We could treat Bayesian construction as a process control problem, where we can continue the proposed critique cycle until posterior stabilize, kind of like events. Lastly, key takeaways. One, use large signal for structure. The tools use tools for numbers can be useful for this particular setting. And also multi-agent framework does improve the performance. Secondly, bigger models are not automatically better. The classic regularization intuition still applies, something to watch out for. That's it. Thank you all for listening.